All right, so we're going to figure out the slope at B and the displacement at the midspan for this structure. It looks kind of similar to the one we had before, except you notice we have some additional loads. Also imagine if you had to do direct integration. So again, you would have to write a moment equation that was valid over the first 2 meters, and then a second set over the next 2 meters. And through the integration process, you would generate 4 constants. You would get 2 with the conditions at A, the displacement 0, the slope is 0, and then you have to match the 2 solutions at the center. I think eventually you would probably get a set of simultaneous equations to solve. And once you had the equations, you'd still have to evaluate. So it is possible. It's not an impossible problem. But if I gave you this on the exam, you probably wouldn't have time to do all that. But you would have time to do, hopefully, conjugate beam. So let's start first. The first step in conjugate beam is to come up with the moment diagram in the real beam. So I'll come over here at A, and I will assume positive shear force. Didn't give myself much room there, and a positive bending moment. And we're going to solve for those 2 values to get started. So we're going to sum moments. A good place to start for moments would be where? Probably at A, right? You wouldn't have to worry about the shear at A, and you should be able to solve for the moment. So we're going to start with that as our opening equation. So summing moments about A using right-hand rule as my positive sign convention. The moment at A is negative. And both these 8 kilonewton forces are also going to create negative moment. So it'll be the force times the distance. The first distance is 2 meters. And the second one has a distance of 4 meters. So I can solve for my moment at A. It looks like it's what? 48? That'll be 48 kilonewton meters. I'll remember from last time we had actually a value. I forgot to point this out. We had values for E and I. You notice this time it says assume E and I is constant, so we don't have to worry about the conversion. The next step would be to find my shear force. So to do that, I'll sum forces in the y direction. There's my equilibrium statement. And in the y direction, I'm going to assume up is positive. So my shear at A is up. That's positive. Both the 8 kilonewton forces are down. So minus 8 kilonewtons minus 8 kilonewtons. So it looks like my shear at A is 16. Any questions about that? Yeah.
So when you ask us one of these on the test, you're just going to tell us that E and I are constant?
Yeah, the statement, it could look exactly like this on the exam. Yeah. I'll either tell you it's constant or I'll give you a value. So let's see if I can squeeze this in over here. So there's the kind of a template for the beginning and end of my shear moment diagram. I've got something going on here in the middle with that force, so I'll add that. So let's see what we'll get. I'll assume positive X, positive shear, and all these units will be in kilonewtons. So what is the shear at A? 16. And we know the change in shear is equal to the area under the load curve, which is 0, so we get no change. It stays 16. We know the slope of the curve is equal to the load. The load is 0, so we have a 0 slope. That's a horizontal line. So we've got something that looks like that. Now, if we go from left to right, what happens? We have an 8 kilonewton applied force. It's down, so how's our shear going to change? It's going to go from 16 to 8. And then the change from here to here is the area of this part of the curve, which is 0, so I'm going to stay at 8. And of course, the slope of the curve is the load. The load is 0, so we have a horizontal curve. So we get kind of a step shape. And you'll see at the very end of the beam, we have a positive shear of 8. Now let's look at the moment diagram. Now, I think you can see this, but I'll say it anyway. One drawback to this approach is, if you don't draw the moment diagram right, well, you're dead in the water, right? You can't go anywhere. Well, you can, but you'll obviously get the wrong answer. So it's not a trivial issue, but don't forget to take some care with the moment diagram. Make sure, check as many things as you can to make sure it's right. So what is the moment at A?
-48.
Yeah, we saw for that, -48. The change in moment is the area in the shear diagram. So over this first 2 meter part, it'll be 2 times 16, that's 32. This is a positive area, so what's -48 plus 32? 16. And the slope of this curve is given by the shear value, and the shear value is constant and positive. This little trapezoidal section. And then over the last 2 meters, the change in shear is equal to the area under the load. The change in moment is equal to the area of the shear diagram, which is 2 meters times 8. That's another positive value, 16, and -16 plus 16 brings me to 0, which we had no applied moment. That's great. The slope of this curve is equal to the load, or the shear. The shear is constant and positive. So there's a little bit of a kink there. So there's your moment diagram. So let's come over here and construct the conjugate beam. So in conjugate space, a fixed connection becomes what? Free. And a free support or free end becomes fixed. Now, I want to remind you that I've had some students just think that you take the beam and you just kind of flip it over. You kind of invert it, and that's the conjugate beam. That's not always true. It happens to be true for this beam, but not in general. Remember, fixed connections map to free to fixed. What does an external pin turn into? Stays a pin. An internal support becomes a hinge, and a hinge becomes an internal support. Those are your 3, or I don't know how many choices that is, about 3 basic categories. So there's my beam. Now again, just imagine taking the moment diagram and sliding it over and dropping it right onto your structure. And when you do that, you might get something that looks like this. This has a value of 48 kilonewton meters, and we're going to now divide it by EI. And this value would be 16 kilonewton meters divided by E and I. And just to remind us, this is 2 meters, and this is 2 meters. Now, this moment is what? Positive or negative? Negative. It's all negative, right? So when we apply it as a load, it's a negative load. Negative load is up or down? Down. So there's our conjugate beam. So now we just have to find what in the conjugate beam. Well, according to this, we need the slope at B. The slope at B would be what here? It would be the shear. So here's the shear at B. It's also a fixed connection. This would be the moment at B. If we found the moment of B, what would that tell us in the real beam? You know? It would tell us the displacement, right? But we want the displacement at the midpoint. So we're going to have to come back and find the displacement here at the midpoint. The first thing we need to do is just find these reactions and then cut the structure. Now, I could find the displacement at the midpoint by cutting the structure and looking at just this left side and find the internal moment, and that would be the displacement. But I'm thinking, since you're going to need to find the slope at B, which is this, you might as well go ahead and get that, and then you might have an easier time working the right-hand side. So first, let's take the whole free body and find the shear and moment there. This is going to take a little bit of time because this is pretty complicated. I might want to break this up into a bunch of forces. So the first one, I'll call it here. I'll call this force 1. That'll be this triangular piece. And then I'll have another triangular piece. I'll call that force 2. And then I'll have a rectangular piece. Maybe call that force 3. So let's first find all those forces. So what is force 1? I'll kind of just sketch it here. It's this little triangular part, right? So the area of that triangle will be 1/2 base, which is 2. So the 2 and the half cancel. So it's just going to be this height. What is this height here of the triangle?
32.
Yeah, it's 48 minus 16. It's just 32. So F1 is going to be 32 kilonewton meters squared over EI. What is force 2? Well, that's just this little triangular piece here. 1/2 base times height. So again, the 2 and the 1/2 and the 2 meters cancel, and I just get this height, which is 16. So this becomes 16 kilonewton meters squared over EI. And then finally force 3, which is this rectangular portion here, which is just base times height. The base is 2, the height is 16. So you get 32 kilonewton meters cubed over EI.
Meters squared or meters cubed?
It should be meters squared because the heights are kilonewton meters and then the bases are meters. So meter times meter squared. And then we'll need all those distances. So let's start by summing. Oh, wait, class is way over, huh? You guys just let me sit here droning on. Sorry about that. Yeah, I got 11:05. Oh, it's just 11:05 now. My watch is super fast. Let me just do this one, and then I'll stop. We'll pick up here on Tuesday. You know what I think I'll do is I'll go ahead and work this out, and I'll post the solution so you can see it. Let's just talk about it for a second. So it shouldn't be too hard to find the moment. Right now, I could just sum all these forces and find the shear, right? So what would that be? You add those together, it comes out to be exactly 80. So that means if the shear, it comes out to be negative, right? It should be negative 80 kilonewton meters over EI, and that is the slope at B, negative. Does it make sense that that should be negative? Well, I think so. I think your deflected shape is going to look something. It's going to look something like this. And at B, that is definitely a negative slope. So that part we could do very quickly. I'm still going to need to get my moment, and then I'll have to come over here and cut the structure and look at the left-hand side.
I got the moment too.
Oh, what's the moment?
224.
It should come out negative.
Yeah, I think it's...
Yeah. That makes sense too, because you get a negative displacement. But I'll go ahead and do those calculations for you, and then what we'll do is I'll cut the structure here, and I'll look at this free body diagram, and all I want to find is the internal moment here to get the midpoint, the midspan displacement.
So you don't have to find the shear there, just the moment?
Well, if I could find the shear there, that would give me the slope at the midspan. But I don't need the slope at the midspan. Well, I mean, this problem, I don't need the slope at the midspan, right? All I need is what? Displacement at midspan. So I only need the moment at midspan in the conjugate beam. So the parts you need in the conjugate beam are described by what you want in the real beam.
So you just need to find the moment at that.
Yeah, I don't need the moment at B to solve the problem. Right? I could have just taken my shear here, and then I could cut the structure here and find the moment of this free body, and that would give me the answer. That might be easier, actually. There's a couple paths to go here. I guess for you, the most important thing is the path of least resistance, whichever one helps you get to the solution. All right.